Alrighty, so we are going to combine 5.2 and 5.3 today. We're going to start with 5.2, adding and subtracting polynomials. But let's kind of remind ourselves what exactly a polynomial is before we go adding and subtracting anything. So a polynomial is made up of terms. Polynomial is made up of terms. Terms, any sort of exponential expression, right? We just talked about what those were in the last chapter, or a real number, or variable, or all of the above. So anything that's a real number or a variable which could or could not be raised to another power, that's a term. So anything held together by multiplication or division. Got some examples here below. 4x, 9x squared, 5 halves z to the 15th, negative y to the third, 1 over z squared, x over y, and 10. Those are all examples of terms, right? What you don't see in any of these is addition or subtraction, right? So it's all multiplication or division. They're all separate. They maybe got some squares, but there's no addition, no subtraction. Alright, when you have terms like this in the first three here, that thing in the front, the 4, the 9, the 5 halves, those are called coefficients. Coefficients. We've been talking about these a lot. This is just kind of a formal definition of these reminders, or a reminder of the formal definition. Sorry, a little dyslexic moment there. But the numerical value in front is usually called the coefficient. So the 4, 9, and the 5 halves. The 1 is in front of these three guys. We have a negative 1 here, a 1 times that, and a 1 times that, right? So there's a numerical coefficient there. You just don't see it. So there is a 1. And then also technically a 10. 10's kind of up for debate depending on how strict you are with the definition of coefficient. Technically, we have an x to the 0 attached to this, right? Now, remember, x to the 0 is equal to 1. So any constant has something to the 0 power attached to it, therefore it is also a coefficient. But, you know, if you didn't want to consider 10 to be a coefficient, you would have quite a few mathematicians who agreed with you. Really depends on your definition of coefficient. So for right now, you could either say 10 is or is not. You wouldn't be wrong, but the other four definitely are. Definitely are. As we just talked about, the 10, since it is all by itself, is considered a constant. It's considered a constant since constantly just 10, right? It doesn't have any variable. It's going to change anything. Therefore, it is the constant value. Any real number without a variable is going to be a constant. Okay, when you start grouping these guys together, you take a bunch of them, whatever you may have, and you put them in order. You can get what we call a polynomial. Poly means many, nomial means terms, right? Nomial or number, so many terms, right? That's what you have, many terms put together. Here is where you rope in the addition and the subtraction. You do not have addition and subtraction in individual terms. Your terms are separated by addition and subtraction. So for example, like in this first one, 9x squared, 4x, and 10, or negative 10, are all terms being added together, right? So 9x squared plus 4x plus negative 10 or minus 10, that creates the polynomial, right? That creates a three-termed polynomial. Same thing goes over here. This is something you might see. It's not as common to see a fraction within a polynomial, but it does happen, right? And this is pretty much how we would write it. Just grouping together. Does it have to be 3? Absolutely not. You can have as many terms as you want. That's why it's polynomial instead of trinomial, right? It's polynomial means many, as many terms as you'd want. All right, cool. Head on down. When you're writing a polynomial, it is common courtesy to write it in descending order of exponent. Descending order of variable. It's what we call syntax. Descending exponents. Not only do you write it in descending exponents, so x cubed, x squared, x, and then 0, you also write it alphabetically. This one is a little bit, again, up for a debate. Some people really like to mix things up so you can see other things, but we usually, 9 times out of 10, write it alphabetically as well. When you have stuff like up here, notice it's x, xy, y. I know that's a little confusing. Or in this last one, it's x, y, z, right? X, y, z. That's alphabetical. And so in the second one, you start with the things that contain x, then you move on to the things that contain y. And if they contain both, they tend to go in the middle. That's kind of how that alphabetical works. Are either one of these technically incorrect if you don't do them? No, but it's common courtesy. It's common courtesy to write them in descending order. Alrighty, so let's look at this polynomial over here, and let's write it in descending exponent alphabetical order. Well, alphabetical is going to be easy. Why? That's right, because they're all y's. So there is really no alphabetical here. But let's write it in descending exponent order. So which one of these terms would come first in descending alphabetical order, in descending exponent order? Good, the y to the 5th term, right? So we'd start with 8y to the 5th. Then we would go down to y to the 4th minus 9y to the 4th. Notice I dragged that negative with it, right? That negative is a part of the term, right? It's being multiplied by a -1. Multiplied part of the term, right? All right, so we got that one. Now let's do third. -6y to the 3rd. Are there any seconds for us to write? No, no seconds. Okay, cool. So then we'll go down to singles. We got y to the 1st plus y. And then any y to the 0s, or in other words, constants. We have one of them plus 12. Fabulous. So we have 8y to the 5th minus 9y to the 4th minus 6y to the 3rd plus y plus 12. That would be the formally recognized correct order of this polynomial. All right. Some other things about polynomials is a few of them have special names, right? You've heard these before, probably. Monomial is one term. Think mono, a mono, like when you take one-on-one. Mono means one. Binomial, which means two, like bicycle. Bi is two. And trinomial, like triangle, means 3. So these 3 are usually identified. So if you have a single term, 4x, you're a monomial. If you have 2 terms, 4x minus 2, binomial. And if you have 3 terms, 9x squared minus 4x minus 2 would be a trinomial. After that, a quadnomial sounds frankly stupid, so we just don't call it a quadnomial. We go on to polynomial. So after that, polynomial is anything 4 plus. Okay, so polynomial is anything 4 plus. So if I were to say what's the degree of this, or if I were to say how many terms in a trinomial, or what's the 4th term in this trinomial, you would look at me like I was crazy, because there is no 4th term in a trinomial, right? So knowing those names can kind of help you out, especially if you know that a certain algorithm or a certain process only works for trinomials, as we'll see in the next chapter. You want to make sure you know what a trinomial is, right? If you know that this is only supposed to work for trinomials, you better know this is only supposed to work for polynomials with 3 terms in it. One last concept about polynomials is something called the degree. The degree has nothing to do with the number of terms. This is just called a name, right? We have a name for some of them. But the degree is the highest power in the polynomial. So this is the degree. Think of it like getting your high school degree, right? Or your college degree. You've got high power, right? So the highest schooling you go, that's what you get your degree in. Same thing for a polynomial. If here I have a trinomial that starts with 4x squared plus 3x minus 9, then the degree would be the highest power I see, or 2. The highest power would be degree 2, right? And that's kind of why we like to write it in descending exponent order, so that degree is very easy to find, right? It should be the first one if you've written it in the highest power order, or descending exponent order. Degree, again, some processes only work for degree 2 or degree 8. Our entire 3rd chapter was degree 1 because they were linear equations. We had no squares, right? So it's very important to look at the degree before you start doing any processes. Alrighty. If you have any questions about any of that terminology, that should have all been reviewed. None of that should have been new. If it is, then if it is and you have a question about it, make sure you get it answered now. Otherwise, we're going to go on to adding and subtracting polynomials. All right. Adding and subtracting the polynomials. Like we discussed, we have some terms, right? We have terms. We're going to talk about what is considered a like term, What makes 2 terms alike? Does anyone know? Pause the video and talk about it. What makes them actually alike? Give me a formal definition. Okay, I hope you paused the video and talked, but a formal definition for a like term is not only do they have the same variable, it's right up here. Not only do they have the same variable, or variables if they happen to have multiple ones, but those variables have the exact same exponents. And when I say stuff like the same exponent, I don't mean x squared and y squared. I mean they both have exactly x squared. And if they have multiple, they look exactly the same. So let's try grouping some of these terms. We've got a couple terms here, a few terms here that we can group. Let's start with what would be a like term in this list to 4x. What would be a like term for that one? Take a look at this list. We've got 4x, 9x squared, 6x squared, y to the 0, x to the 6th, 1, 9x, 8y, and 15. Well, obviously, none of the y's are going to be like terms, right? Because that's not the same variable. So it wouldn't be a like term. But let's take a look at those x's. Looks like the only one with the same power would be 9x. So those two guys are like terms. Awesome. So we can cross those guys out. Found all the like terms there. Next up we got 9x squared. Again with the x's. That's not in lime green because gross. Blue, let's write in dark green. So 9x squared. We're going to look for anything that has just an x squared. Well, we've got this 6x squared, right? And do we have anything else that is a square? Doesn't look like it. So those are the two terms that are alike because they both have an x squared, right? Just because the other two had an x does not mean that the green and the red are like terms, right? They're definitely not like. All right, let's go to the next one. We got y. What would be the same as y? We got one over here, 8y, right? So y, 1y, and 8y. Those would be like terms. Looking good. There might be others, but it doesn't appear to be so. All right, last four. We've got y. We're actually going to come back to y. No, we aren't. Let's do it right now. Y to the 0. What would be the same as y to the 0? This one's kind of a trick question. Would anything be the same as y to the 0? All right, if you said no, I'm sorry, you're mistaken. You're mistaken. I'm going to write this in orange because we already have red. Remember, what's anything to the 0 power? What's anything to the 0 power? It's 1, right? So 1 is a like term. We always want to go in simplest form. If you don't have a term in simplest form, then you can't see what's alike to it, right? So not only are those two alike, but since they're both numbers and they have no variable, quote unquote, like have no variable, right? Because y to the 0 just transfers down to 1, then 15 is also common. It's also a constant. So these three are considered constants. All three of them are like terms. And then we have one more. And because we have one more, we probably realize that it doesn't have any like terms. X to the 6th, right? Nothing over here else has x to the 6th. And we have all of our like terms. All right. If you have any questions about like terms, make sure you pause the video, get them answered. Cool. So now we're going to do something you also have probably heard of before. We're going to combine like terms, combining like terms. If terms are not alike, we cannot combine them, right? So it breaks down to the distribution rule. Really it does. When you have two alike terms, like 4x squared and 6x, then what you can do is you can say 4x squared plus 6x squared. I'm going to take out the x squared. I'm going to take it out from both of them. I'm reverse distributing, right? If I were to go backwards, then I could distribute the x back in. I get back 4x squared, 6x squared. Because when I do that, I notice that now I just have 4 plus 6, which is 10. So I can reduce this down to 10x squared. If those x squareds did not match, then I couldn't take them out, right? I couldn't take them out together, so I couldn't break it down, or I couldn't pull the variable part out and combine the coefficients. Do you have to list out this way every single time? No, but you should know that's what you're doing, right? You are pulling it using the distribution property to combine like terms. In order to actually do that, though, as long as the terms match, then you can just combine the coefficients. That's essentially what you're doing. So let's practice that. Let's add these two polynomials by combining like terms. Let's combine these like terms. So I've got 4x squared plus 3. That's a nice binomial. And I've got 5x squared plus 9. That's another nice binomial. So two terms is a binomial, right? They both have degree 2 because the highest exponent I see is 2. Let's go ahead and combine those. So which terms would be alike? Well, the x squareds would be alike, and the constants would be alike, right? Constants would be alike. Notice we have no x terms, and that's totally fine. You've probably seen stuff like this before, where there's missing terms, and that's okay. Remember, all we're doing is adding. It's not like we're factoring or anything. So we just need to combine what we see that is alike. Let's go ahead and do that. We'll add the coefficients of the x squared. That gives us 9x squared. And then we'll add the constants, plus 12. And we arrive at our new binomial. Will you always end up with a binomial? Absolutely not. Nope. If you start out with 2 binomials, there is no guarantee you're going to end up with a binomial. It has nothing to do with that, right? You just combined what is alike. What is alike? All right. You guys go ahead and try this second out. Add this trinomial to this trinomial, if you can, right? If there's anything actually to combine. And then I would also like you to identify the degree of these trinomials. I take that back. Identify the degree of your answer. So first, add them, if you can, and identify the degree of your answer. Alright, I hope you paused the video and actually tried this out. I have 2 trinomials here, some like terms. 6x squared, 3x squared. I end up getting 9x squared. And then I have 7x and negative 6x. Combine those. I got to be careful when combining those, right? Because I have a negative 6x. So all I'm left with is a positive x. And then last but not least, we'll use this right now. We'll use purple. I have a negative 9 plus a negative 2, which is a negative 11. And there's my new trinomial. The degree of this trinomial is the highest power I see. The highest power would be 2. The degree would be 2. Awesome. Alrighty. Let's do the same thing with subtraction now. There's only one additional step we have to worry about. You may have heard it before. It's called distributing the negative. So notice distribution property playing a lot in adding and subtracting these polynomials. So I've got these 2 polynomials here. 7x squared plus 5. 7n squared plus 5 minus 6n squared minus 6. And I want to subtract them. But when I subtract them, remember, parentheses are super important. Parentheses are telling me that I don't want to just subtract the 6n squared, right? That's not what I'm saying here. I want to subtract the entire second binomial. So if I want to do that, then either I have to mentally calculate that I'm subtracting both times, or I can just make my life easier by distributing out that negative and making it an addition problem. So if I do that, then I can get rid of the parentheses. N squared plus 5 was unaffected, right? But in this next second term, it's negative 6n squared plus 6, right? Because now I'm subtracting that negative 6, or I'm adding the 6. So if I do that from the get-go, if I distribute that negative, then I don't have to worry about whether I'm subtracting or adding, right? I can just change it to a combining like terms problem. From there, I notice that I have 2n squareds. Oops, should have done the negative as well, which leaves me with an n squared. 7n squared plus negative 6n squared. In other words, 7n squared minus 6n squared leaves me with an n squared. And then I also have 2 constants, which gives me a plus 11. Alrighty. Once again, I want you to go ahead and try this other subtraction problem on your own. Give yourself about 30 seconds, and then we will do it together. Alright, so I hope you had some time to try this one on your own. We're going to start by distributing that negative. And when I distribute it, it's got to be to all 3, right? Because I want to subtract that entire trinomial, not just the first term, not just the first 2 terms. I want to subtract everything there. So I'm going to rewrite this this whole expression problem as a new as an addition problem. The first trinomial was unaffected. It was unaffected by that, so it remains negative 6m squared plus 5m minus 9. The second one, though, becomes minus 4m squared minus 3m plus 10. And now I will combine some like terms. I notice I have a negative 6m squared and a negative 4m squared. Those combined give me a negative 10m squared. I also have a 5m and a negative 3m. Combine those two, that's 5 plus negative 3, or 5 minus 3, so plus 2m. And then lastly, I have a negative 9 and a positive 10 constants that I can combine. Negative 9 plus 10 is a positive 1. And there's my new trinomial. Once again, in every single one of these examples, we ended up with the same size, but that is not a guarantee. You're only looking for things that combine together. Sometimes things don't combine together, and that's okay. That's okay. All right, so that was adding and subtracting. Like I said before, we're going to do 5.3 or 5.2 and 5.3 today. But if you have any questions now about polynomials, degrees, combining like terms, monomials, trinomials, binomials, what a like term is considered, what a coefficient is, constants, any of that jazz, any of the terminology we use with this, make sure you stop and get your questions answered before we move on to 5.3, which is about polynomial functions. Okay, so let's move on to 5.3, polynomial functions, graph, and composition. Now, polynomial function, remember when we were talking about linear functions, it's a big sounding word for something that really doesn't change much. Yes, we had to talk about domain and range, and that got a little tricky, but remember a function is just 1 to 1. 1 to 1, sometimes written like this, which means for every 1x, there's only 1 y. That's it. For every 1x, there's 1 y. So if I were to put in a value for x, I'm going to get one answer. That's all a function is, right? So for linears, we were testing that out a lot. We tested that out with a lot of things of degree 1, but it actually is the same idea no matter what degree you have. In other words, for degree n, no matter how far up your polynomial goes, whether it's like 100 or 1,000,000 or whatever, it has to follow that same rule. You can only call it a function if you plug in a number and you only get one out. That's really what a function is. Remember, this is called function notation. F of x, it is not fx. F of x, right? So f of x is some sort of polynomial, and that takes place of the y variable, right? It takes place of the y. So if you've decided something is a function, you can see that it is 1 to 1, then you can replace that with f of x, no matter what degree polynomial you have. Alrighty. Let's recall something else about function notation. Remember, you can evaluate using function notation. So if I see something like this, where my function is now f of x is equal to 4x to the third minus x squared plus 5, then what does this thing right here in A mean? What question is it asking? Do you remember? Pause the video and talk about it if you need to. Alrighty, so what it means is that it's asking you to evaluate 3, right? It's asking you to plug in 3. In other words, the question it's asking is, what is f when x is 3? That's what it's asking. So we just take f of 3 and we plug it into that equation. We had 4 times x cubed, so now we've got 4 times 3 cubed. Notice I put parentheses, right? Otherwise it's not 43 cubed all of a sudden. Minus 3x squared, minus 3 squared plus 5. I don't want to add a 3, I want to replace the x with 3, right? And now I'll do PEMDAS and I'll solve this. So I'll start with some exponents. I have 4 times 27 minus 9 plus 5. 4 times 27 is 108. Minus 9 minus 5 plus 5 is 104. So it looks like f of 3 is 104, right? When x is 3, f is 104. That's my answer. So f of 3 is equal to 104. Go ahead and do the same thing for f of negative 4. Go ahead and try that out real fast. You don't even need to pause the video because it's not going to take that long. Alright, now you probably needed some more time, so if you do still need some more time, go ahead and pause the video. Definitely pause the video. It's hard for me to gauge how fast you guys are working from, you know, my house. But so if you do need more time, please go ahead and pause. But I'm going to go ahead and do it. So for f of negative 4, whoa, maybe I can do this. F of negative 4. And I'm going to do the same thing. I'm going to plug in negative 4 every time I see an x. So 4 times negative 4 cubed minus negative 4 squared plus 5. And notice I'm putting parentheses around that negative, right? It means something different. Putting it around the negative because that's a part of what I'm plugging in. It's not a part of the original definition of the function, right? And we talked extensively in the last section about the difference between the two versions, putting in the negative inside parentheses or negative outside the parentheses. And we'll go ahead and solve that. Negative 4 to the third is negative 64. 4 squared is going to be, negative 4 squared is going to be positive 16, so minus a positive 16 plus 5. I'll do some multiplication. That's going to be negative 256 minus 16 plus 5, or negative 67, negative 267. So f of negative 4 is negative 267. Awesome. Alright, so that's just a little reminder on functions and kind of how they work. Now let's talk about functions and modeling data. We talked a lot about this, again, with linears. We're going to do it with higher powers now. So let's check out this real-life example. The number of U.S. households estimated to see and pay at least one bill online each month during the year 2000-2006 can be modeled by this polynomial function, polynomial function here, where x equals 0 corresponds to the year 2000, x equals 1 corresponds to 2001, and so on up to x equals 6. And p of x, right, it's not px, p of x is in millions. Use this function to approximate the number of households that paid at least one bill each month in 2005. So, they kind of define how this function works. They give us two bits of important information. Right here they tell us where x corresponds to this jazz, right? And then they also tell us that p of x is in millions, right? They usually always tell you about both parts of the variable. Tell you about the variable you see on the right-hand side and the variable you see on the left-hand side. Sometimes they're not always on different sides, but they tell you about everything you see in the problem. That way, you can use that information to figure out what you need to do. Do you need to plug in for p or do you need to plug in for x? Well, here it says we want to find how many households in millions have paid at least one bill each month in 2005. So what they told me was a 2005 year, and the x corresponds to the year, right? And you'll see this break down a lot, especially with years and budget reports and things like that, where x equals 0 represents the starting year, and then from that they build up, you know, to those years. So what is x when it's 2005? What would x be? That's right, x would be 5, right? Years since 2000, 5 years. So let's go ahead and plug in 5 to our function. So we want to find p of 5. It's equal to 0.808 times 5 squared plus 2.625 times 5 plus 0.502 as a constant. Alright, again, I'm going to use my PEMDAS, so I'll start with those exponents. 0.808 times 25 plus 2.625 times 5 plus 0.502. Now I'll do the multiplication. I end up with 20.2 plus 13.125 plus 0.502, and then I'll add those all together. It's 33.827. 33.827 is the answer to P of 5. But what is the answer to the actual problem? What is the answer to the actual problem? Right? It's P in millions. P of X is in millions. So it'd be 300 or sorry, be 3.827 million households paid one bill in the year 2005, right? So that's how we would represent. This would not be the part we want to box. We'd want to box this part because that is actually our solution, our answer. Now, something I see happen quite a lot, I always see people give me rolls of the eyes whenever I try to solve out problems like this. I go step by step, right? Yes, I'm fully aware that your calculator can handle a polynomial like that, but 9 times out of 10, people mess it up. You mess it up. It's so easy when you're giving the calculator 500 things to do at one time. It is so easy for you to tell it wrong. It's so easy for you to accidentally say 5 times 2 instead of 5 squared. It is so easy to accidentally forget a negative or to miss a number or something like that. So when people say, oh, Miss K, she's taking so long, I'm so smart, I can do this in my calculator, I actually laugh at you and I feel bad for you because you're entirely dependent on your calculator, and if you mess up how to enter it, your whole thing's going to be wrong and you're not going to know why. So I strongly recommend, hintity hint hint, that you should break it down like this. Do it yourself. If you do it yourself, you can find your mistake, you can make an easy fix. But if you just trust the calculator, you're going to be sitting there for 45 minutes wondering why your homework doesn't match up with what your calculator says, right? If your two machines can't talk to each other, you have to be smart enough to figure out why. So don't use calculator error ever in my class. If you say I had a calculator error, then I will laugh at you and I will actually kind of cry for you because you really should be smarter than that. Calculators are great inventions, and yes, I know they're on your phone, but please don't let them be smarter than you. That's what I'm trying to say. Anyways, so we had a function, we used it to solve a problem. That's how we use this to model data. Alrighty, let's talk about adding and subtracting polynomial functions. We did this with polynomials in the last problem, and luckily it's no different. Remember, functions are just fancy polynomials. They're just fancy polynomials. Because they're fancy, sometimes we write it fancy, that's all. But if you have two functions, call it f of x and g of x, and you want to add them, then you say f plus g of x, which relates to adding the two functions. If you want to subtract them, you want to take them and subtract them, right? So their names are f and g, right? F of x and g of x. So if you want to subtract f minus g, that's what you say. You say f minus g of x. Yes, that's a lot of parentheses, but it really just corresponds to I want to subtract these two functions. So let's try that out down here in 3.1. Excuse me. We have this function here, f of x is equal to x squared minus 3x plus 7. Pause right now and talk about what kind of polynomial is this? What kind and what degree? What polynomial, what kind and what polynomial? Kind and what degree, sorry. Alright, I hope you said a trinomial of degree 2 because that would be the only correct answer. It is 3 terms and has an exponent of 2 as its degree. Same thing goes for g of x, which is equal to negative 3x squared minus 7x plus 7. And we want to find these three expressions, these three, well, evaluations, really. Alright, in A we have f plus g of x. What does that mean? What is it telling us to do? F plus g of x. That's right, it's telling us to add the functions, right? It's really not all that different. So we want to add these functions, f plus g, right? So this kind of correlates to the same thing as f of x plus g of x, right? And if I substitute what I know about f of x, I know f of x is equal to x squared plus, I'm sorry, not plus, minus 3x plus 7 plus negative 3x squared minus 7x plus 7 was g of x, then I can tell that this looks exactly like the problems we just did before, right? So you just substitute in. Remember, those fancy functions, they're just polynomials with names. That's all they are. We can now combine like terms. I've got these x squareds that I can combine. I end up with negative 2x squared. I've got these x's that I can combine, a single x, and with negative 10x. And lastly, I've got these constants I can combine. 7 and a 7 gives me a plus 14. So f plus g of x, I do not have x anymore, or I do not have f anymore, I do not have g anymore, I have f plus g of x is equal to negative 2x squared, minus 10x plus 14. There we are. Let's do the same thing with subtraction, but if you have any questions on what we just did there, make sure you pause the video and get them answered. Alright, same thing with subtraction. This time we have, let's go ahead and just, yep. Okay, so this time, instead of adding the two functions, we're going to be subtracting the two functions, f minus g of x. So f of x minus g of x. Again, we'll just substitute what we know. F of x is still x squared minus 3x plus 7. And notice I'm writing parentheses every single time so I can keep my thoughts in order. Over here, they weren't vital, like we could have gotten away without writing them. But now when we're subtracting, remember, we have to deal with that negative. We have to deal with subtracting the entire polynomial g of x. So I want to make sure I put it in parentheses to remind myself to actually do that. Squared minus 7x plus 7. So I just plugged in f of x and g of x. Now I'll go ahead and subtract those. I'll start by distributing that negative, just like we just talked about a few minutes ago. F of x is unaffected by that. So negative 3x plus 7. But now g of x is plus 3x squared plus 7x minus 7. And let's go ahead and combine those like terms. Got some x squareds here. That becomes 4x squared. Some x's here. Now it's not negative 10 because the 7 is no longer negative, right? It's going to be positive 4x. And then we've got 7 minus 7, or 0, which we could tack on, but is unnecessary. So we end up with a binomial instead of a trinomial of degree 2. 4x squared plus 4x. Alrighty. That was subtraction. Notice the only thing different was the subtraction sign, right? Everything else was just subtraction of polynomials. Okay. The last thing we want to do is evaluate an addition, right? So now don't worry. This isn't anything more, right? It's just f plus g of 2 instead of f plus g of x. And we already discussed today what it means to have f of something, right? Where did it go? Where was f of something, right? We had f of 3, right? We had f of 3 and we just plugged in 3 for that. So now, since we already have a function f plus g, we already added them together, we can just evaluate it at 2. So we'll find let's use a color you can actually see. F plus g of 2, which means take f plus g and plug in 2. That's why I didn't name it something else. I didn't name it h. I didn't write out that it was f or g, right? It wasn't one or the other. It was f plus g. Now I can use it to evaluate 2. So let's go ahead and do that. Negative 2 times, instead of x, I'll write it 2. So negative 10, instead of x, I'll write it 2, plus a constant of 14. And I'll solve via PEMDAS. So 2 squared is going to give me 4. Negative 2 times 4 minus 10 times 2 plus 14. And then we'll do some multiplication. Negative 8 minus 20 plus 14. Finally, we have negative 28 plus 14 is negative 14. Is our answer. So f plus g of 2 is negative 14. So then notice these concepts are just kind of building on each other. We're learning how to add stuff together, evaluate stuff, and then we do them both at the same time. It's not like we have to remember 500 different things. We only have to remember these certain, like, 5 elements and then put them all together, right? Alrighty. Going along those lines, we're now going to talk about something called composite function. Because this is a polynomial, and it's not, or these are polynomials, I should say, we have more than one. Because they're polynomials and they're not just numbers, we have this idea that we can plug in multiple times, and that's what a composite function is. Think like composed of, right? When you compose things, you put in a whole bunch of things together, right? So when you compose a mixture for a solution, you're mixing a whole bunch of stuff together. That's what we're doing here. We're going to do a composite. Now, be super careful. This is not multiplication. It is not multiplication by any means necessary, okay? And some people mix that up because when they see the symbol for composite, this little open circle, they think multiplication. So be very careful. If you have tiny handwriting or maybe sloppy handwriting, draw your composites big, okay? Draw them big. But really, it's an open circle. This is a multiplication symbol. That is a composite symbol. The top is composite, the bottom is multiplication. Alrighty, sometimes you'll see it like this with that symbol. Usually you'll see it like that in my class because that's the accurate one. But what it means is essentially this. Take one function and evaluate it inside another function. Now we've kind of already done this. We've already done this. If you remember, we had something like g of a plus 1, right? And we would take that expression and we would substitute it in for x, and then we would simplify it down. That is exactly what composite is. That is the only thing it is, only now it's considered a function. So instead of writing the whole function in the parentheses, we're just going to write the name of the function in the parentheses. So in other words, in this case, this was f of x, and I put it in instead of writing a plus 1, or it would be f of a, but instead of writing the whole function out, right? So we'll see what that looks like with numbers. Let's try it out. Alright, so I've got f of x is equal to x squared, and g of x is equal to x plus 3. Let's find f composed with g of x. That's how you would say that. F composed with g of 4, actually. F composed with g of 4. So they're asking us to do quite a few things here. First, they're asking us to compose them, and then they're asking us to evaluate it at 4. So let's try doing that. Now, an important note. When you see it in this format, f composed with g, you may be wondering, does that mean I plug g into f or f into g? You always plug the second one into the first one, no matter what, right? And we can tell that later on they're going to ask us to compose g with f, so they're going to ask us to do the reverse as well. So make sure you always do the second one into the first one. Alright, so in other words, if I want to compose f of g, f composed with g of 4, well, let's do x first so we can actually get the expression. So f composed with g. Another way to see this is as f composed with g of x, or f of g of x. F of g of x. And you can see how it's g of x is now sitting inside where x goes, right? It's g of x, right? All the way inside. So let's do that. So if I want to do that, then f, let's rewrite it as we've seen before, right? As we've done this before. What was g of x? What should I substitute for g of x? What was that equal to? It's equal to x plus 3, right? So now I want to plug in x plus 3. I'm composing this inside f of x. So now I'll take that, which means the same as it did any other day of the week. Whatever's in the parentheses, I replace with x. So if f of x is x squared, then f of x plus 3 is x plus 3 squared. And I have my composed function equation. So all I did was take g of x, 3x, and I stuck it inside for x. That's all I did. There's my composite function. Now I'll evaluate that at 4. So I want to take, I don't want to do it that way. So now we'll say f of g of x, not f of g of x, f of g of 4 is equal to, well, again, that means the same thing, right? No matter what we're talking about, putting something in those parentheses means replace your x with this thing, right? Whatever it may be. So this would be 4 plus 3 squared, which would be 7 squared, which would be 49. All right, so f of g of 4 is equal to 49. Alrighty, let's try the other way around. So now we want g of f of x, and which means we're going to put g inside of, we're going to put f inside of g, not g inside of f. So let's go around the other way. We'll go this way. Well, f of x was x squared, right? They were the same thing. So I can rewrite it like that, right? If I so choose. That's an additional step. If you don't want to do that, you don't have to. But that reminds you what's going inside, right? Which one are you actually substituting in? So you can definitely take that step if you need to. And since g of x was x plus 3, this notation right here means I want to take every x I see and replace it with x squared. So I now have x squared plus 3. Since there's no x on this 3 part, I don't have to add it. I don't add x squared there, right? So I just plug it in for x. Awesome. We have our composed function. Slightly different than this one, right? Now the 3 is inside, here the 3 is outside. Let's see how that changes our answer. So f of g of 4 now, I'm going to substitute 4 in for x, which would be 4 squared plus 3. This time I'm going to square first, right? Square first is 16 plus 3, or 19. Wow, that's quite a different number when you compose g of x into f of x versus when you compose f of x into g of x, right? Two very different numbers. Alrighty. Go ahead and pause the video here and try out this next composition yourself. You're going to need to find f of g of x and then f of g of 2. So remember, make sure you're doing the right plug-in. Make sure you're going the right direction. But go ahead and give it a try, and then we'll reconvene in just a minute. Okay, so I hope you've had a try. Hope you tried it out yourself. Remember, that's the worst thing you can do is not try these problems, because that makes your homework really hard and long and complicated. But let's see if we can do it ourselves, just in case. So f of g of x. F of g of x. Well, I need to make sure I plug it in the correct order. So which one was that? Was that was that taking g and putting it in f, or was that taking f and putting it in g? Which one was that? I hope you said it was the second one, taking g and putting it inside f, right? We want to take g and put it inside f, right? Always take the second one and substitute it into the first one. Think f of g of x, right? F of g of x. So let's go ahead and do that. F of g of x, well, g of x is x squared plus 5. So x squared plus 5, right? I'm plugging it into f. And f was 4x plus 1, so I'm going to keep the 4, I'm going to keep the minus 1, but now I'm going to change x to x squared plus 5. X squared plus 5. And then I'm going to go ahead and simplify. But just in case, I want to make sure we go over that one more time. Take whatever is in the parenthesis and substitute it in for x, right? And then we simplify. 4x squared plus 20 minus 1 is equal to 4x squared plus 19. And that would be f of g of x. Now to find f of g of 2, I'm just going to take that function that I found and plug it in. So f of g of 2 is going to take every x I see and replace it with 2. It's the theme for the day, replacing stuff, right? Replacing. And I'll start with I'll do PEMDAS in order. Exponents first. 4 times 4 plus 1 is equal to 8 plus 1, or 9. I'm sorry. Just kidding, Miss K. 4 times 4 is 16, plus 1 is 17. JK, LOL. Alright, so we get 17. Cool. That is composite functions. So far we can add functions, subtract functions, and now we can compose functions. Which is awesome. If you have any questions at all, please make sure you stop. We're going to talk about one more thing today. We're going to talk about some graphs of some functions. But if you have any questions, let the sub know now. Alrighty, so the graphs of polynomial functions. Now, we've seen a whole mess of them in linear form, right? We talked about linear forms extensively in Chapter 3. They're straight lines. These are what we call the degree ones, right? Degree 2s are called quadratics, and they make this shape right here. I hope you remember this shape. It's called a parabola. We'll see these a lot a little later on, but right now we're just going to kind of look at the shape. And then if you go up to degree 3, it's a cubic. This is what we call cubic, and it makes this sort of swooshy thing. And then as you bounce higher and higher, so degree 4s if you want to put it up here, a degree 4 ends up looking kind of like this. It's like a W. Degree 5 is more like a cubic, but it's got the W in the middle. And then it just keeps adding bumps in the middle. So degree 6 would have 2 bumps in the middle, degree 7 would have 2 bumps in the middle, degree 8 would have 3 bumps, degree 9 would have 3 bumps, and so on and so forth. So these are really the 3 basic shapes you see. And then you've got the other ones that are like square roots and things like that, which are pretty cool too, but we're not really going to talk about them this time. We're going to go ahead and graph some of these guys, but the easiest way to graph works for any polynomial, any function, is to make a table. I know you guys have talked extensively about other ways to graph. We definitely did in Chapter 3 with slope-intercept form, with point-slope form, with finding the intercepts. That's all fine and dandy. But the easiest way to graph any function is to make a table of your choosing. So we make a table, right? So just make a table, x comma y. And then you get to pick whichever values you want. Now, I strongly recommend, since we have a 4-quadrant graph, right, all 4 quadrants, we're going to need some negative numbers for x. So let's plug in some negative numbers, -1, 0, and 1. And then we're going to use it to graph. Now, in order to use this table, I'm going to go up to my function, and I'm going to evaluate the x's I just chose. So if I chose -1, 0, and 1, I'm going to evaluate f of -1, f of 0, and f of 1. I'm going to find out what those corresponding y values are, right? Because remember, a solution to an equation is a point on the graph. That's how you graph the function, right? So f of -1 would be -1 squared, or +1, right? F of 0 would be 0 squared, or 0. And that would be 1 squared, which would be 1. So it looks like for x equals -1, y is going to equal +1. So there's my first point. I've got 0, 0 as my next point. And I've got 1, 1 as my next point. So from there, I can kind of eyeball it and draw myself the parabola. Alrighty. Not very difficult, right? So you plug in some points, you evaluate them, and then you treat this like a point. So -1, 1. Let's do the same thing for f of x equals -x squared. Be super careful. What is happening when we evaluate? Be super careful. Watch those parentheses. Watch those parentheses. But let's make a table. Yeah, let's make a table. X comma y. Let's do this in like blue. There we go. X comma y. I like to choose the same 3 x's every single time because I've got a -1, a positive, and a 0, right? But if you don't want to choose those, you don't have to. If you know that this graph's going to be, you know, around 15 feet in the air, then start with 15, right? If you have that sort of intuition, go for it. Otherwise, these 3 tend to work out most of the time. Sometimes they don't. If you need more, just keep going until you find stuff that's actually on the graph. All right, let's plug it in. So f of -1 and f of 0 and f of 1. Alright, so -1 squared. You see how that happened? The negative is a part of the function. So when I plug in -1, that is not a negative on the inside. It is a negative on the outside. That's what I meant by be careful, right? So now we've got negative of +1 or -1. F of 0, whoops, would be -0 squared. 0 squared is just 0, and there's no such thing as -0. 0 has no negative or positive value, so it's just 0. And last but not least, we have negative of 1 squared, or negative of 1. So we end up with the points -1, -1, 0, 0, right, 0, 0, and 1, -1. So I can kind of graph where I see this going. Now if I didn't do the negative side or I didn't do the positive side, I might be inclined to think that it goes in a straight line, right? So you always want to do both sides of the graph. You want to do a negative x and a positive x so that you can see what kind of mirror image you're getting. If it is a mirror image, if it's linear and it goes in a straight line, you still need one on both sides of the graph. So make sure you always pick a negative value as well. That way you can see both sides. Alright, you guys go ahead and try out this last one. See, and remember, it's just plugging in, so even though it's not squared, Doesn't matter. You're taking a table and you're going to plug in f of whatever you choose, right? Try to choose 3 values. Go ahead and give it a try now, and then we will reconvene and we'll talk about the answer. Alright, so I hope you had a chance to try this. If you didn't, then you need more time. Make sure you pause the video. Alright, so I choose my x and my y. I'm going to even choose the same values, because, you know, why not? -1, 0, 1. And I'm going to plug those in. So f of -1 is going to equal -1 cubed minus 2. And notice this time the negative part is in the part that I'm plugging in, so it goes in the parentheses, right? If it's not part of the function, you don't put it in. You don't put it outside the parentheses. That would be -1 times -1 times -1 is -1. Minus 2 would be -3. Now I'll do f of 0. Should be 0 squared minus 2. That would be 0 minus 2 or -2. F of 1 is going to be 1 squared minus 2 or -1. So go ahead and draw that. Back 1 and down 3 would be right about here. 0 and down -2. And -1 or +1, -1. Now you may be thinking, oh my gosh, this is linear, cool, straight line, right? But remember, when you have a degree 3, it looks like this little swirly. So what I just did was found this part in the middle, that little swirly linear part. And so when I draw this, I want to make sure I kind of go whoosh, kind of like that. Maybe not curving back, but let's try that again. So I want to go whoosh. No. Really? Okay, fine, we'll go down. And then through here and down. So it's kind of a whooshy, right? Because it's a degree 3, not a degree 1. So remember, you kind of have to know the basic general patterns as well. I'm not going to give you anything we haven't talked about, but to get the actual shape and where it is on the graph, you got to make that table. Alright. That is the end of the notes today. We've talked about a lot, 2 whole sections. So we talked about adding and subtracting polynomials and all of the things that are incorporated with that. We've talked about adding and subtracting functions and all the things that are incorporated with functions. Talked about composite functions and now graphing functions. So make sure if you have any questions, you get those questions answered. If you missed anything, you can feel free to rewind the video, write it down again, or go ahead and start your homework. And I will see you in 5.4.